There we go. Okay, hi everybody. Welcome to our May Data Science Education webinar of 2018. This webinar is being made available through the Concord Consortium, a nonprofit educational technology laboratory based in Concord, Massachusetts, and also in Emeryville, California. You can learn more on our website, concord.org/meetup. I'd like to introduce you to our facilitator, Dan Damelin, who will be tag teaming with me, Natalia St. Clair, today. We'll be sharing our work about the Concord Consortium's NSF-funded project, InquirySpace. The InquirySpace premise is that students should learn science the way that scientists do, using InquirySpace learning. Dan will explain what that means in the context of data science education shortly. A recorded version of this webinar will be made available on YouTube, and we'll email you details about it through the Eventbrite after the event. If you're comfortable sharing your name and face, please turn on your web camera during the webinar so that we can see you. I'd also like to emphasize that the format of this webinar is participatory by design. This means that we'll work together to decide the conversations, connections, and activities we want to discuss today. I will be facilitating the live questions that you have, and I will also be managing the text-based questions on Zoom chat. Dan will explain more about that in just a few seconds. And for those of you just joining us, I see a few new faces. Welcome to our webinar. Our speaker is Dan Damelin, who will be speaking about the InquirySpace project at the Concord Consortium. Dan, I'll let you take it from here.
Thanks. I want to also mention on the call today, or on the video chat, Tom Farmer is here, and he is also part of the InquirySpace project. Doing curriculum design and data collection. He has been, I believe, in the classroom earlier today, or will be, and he's muted.
Sorry about that. Every other day but today.
Every other day but today. All right, well, we are fortunate to have Tom with us. So feel free, Tom and Talia, who are both part of this project, to jump in and clarify and or add to the conversation. It's going to be relatively informal today, and we're going to try some stuff that I don't know if it will work, but we will see. And I wanted to talk about this particular project called InquirySpace, and it's InquirySpace 2 because it's actually a follow-on project to an original project. And I'm going to start off with a quote by a colleague of mine and friend, David Hammer. And I remember talking to him once about, this project we were doing and trying to, help people do inquiry-based science. And he just thought it was sort of absurd. Where talking about inquiry-based science is like saying water-based swimming. But this project, the idea is, we want students to have the experience of doing science to learn science. And to do that, the first project was about mainly designing tools and other kinds of things that would be helpful and curricular supports. And this project, we're sort of broadening out and looking more at the classroom environment. In terms of our initial thinking about this, we're thinking that students go through or have 4 sort of aspects to doing their exploration. And I don't want to call these phases because we don't really think of them as sequential. Oftentimes, especially in the beginning where students are messing around and trying to figure out what can I do with the instruments I have, what can I measure? We're trying to get them to a point where they can do their own experiments, design experiments, collect the data, analyze that data, and come up with scientific explanations. Now this project, the original project, InquirySpace 1, started before NGSS, but we feel that it fits really well with the NGSS science practices, in which we have the various practices that connect in with these different aspects of the experimentation that students will be doing. So the impetus for the project, we were thinking about what are some of the obstacles that people have to kind of inquiry approach to teaching science. The first is time. It actually really does take some significant time to let students make mistakes and discover things for themselves about the process of trying to understand phenomena, about what are the limitations in their data. Once they have data, how do they go about doing the analysis? And with real world data, there's a lot of variability to consider. The other piece are the tools. So students, there are a lot of tools that are out there that support students. We've seen there's sensors, and those sensors have their own software for doing data collection. And there are simulations, which are typically separate and on their own. And then there's sort of data analysis tools, which often people are using spreadsheets. That's really the most common thing that people are using for doing that. And part of what takes a lot of time is understanding, how do I use all these different separate tools that ideally should be working together? And so part of what the InquirySpace project has done is we've created an environment in which, sort of InquirySpace, that integrates the sensor data collection, simulation data, generated data, and intuitive data analysis environment that's much more exploratory and easier to use than typical spreadsheets. And you'll hear more about that later. And of course, the last piece is more pedagogical than technical, in which students just they're not trained in this kind of way of thinking about approaching problems and solving problems and collecting the data. Now, one of the things that we're trying to think about in terms of how does this connect with the data science education webinar series, is there's certainly data involved that students are collecting. And the question is, is it data science, the kind of data processing that they're going to have to do? Are there ways that we could collect the data that would lean it more toward data science type data moves? Tim, I think everyone remembers from the data science education conference that we had, your smells like data science comment there. And so the question is, does this sort of pass the sniff test of smelling like data science? So we're going to talk a little bit about that as we get into something that we're going to try together. So that last piece is, how do we get students to the place where they have, the knowledge about the tools, the data analysis skills, and the way of thinking about asking questions that will allow them to be successful in learning science by doing science. So we have a sort of 5-step curricular on-ramp that we're developing. We're developing one in physics, one in chemistry, and one in biology, with the intention that this is educative for both the teachers and the students, and that at the end of this, students have the skills and teachers have the confidence to allow students to do more exploratory work in terms of learning science. Less cookbooky type labs, more student-driven, student design type work. This is a 5-step curricular on-ramp, but as we've been working on this, it's been kind of evolving into various kinds of steps, but I think the general approach is still there, but I'll talk a little bit more about that. So the main thing is that we want to frame our explorations around some phenomena and a motivating challenge. So that connects very much to the NGSS approach of exploring phenomena, phenomena-based type or project-based learning. The scaffolding that we provide will fade over time, so students start with a much more heavily scaffolded interaction with the tools and simulations, and eventually they're designing their own experiments. And so in physics, we started, I'll talk about our physics sequence. we started with a motivating context. We had a sort of ramp game, and we told them that you are eventually going to be presented with a challenge, such that you're working on a movie set, and the director has decided there's going to be a scene where a car is rolling down the hill. It's going to go along a flat for a certain amount of time, and then a tree is going to fall right in front of it just as the thing stops. It's going to be very dramatic, and you're in charge of producing the scene. You got to make it happen. And so one of the things that you're going to need, and the other thing is that this director, very fickle. Sometimes, she doesn't know what time of day, when the lighting's going to be, what hill is going to be used, how far up the hill, maybe which kind of car, all these kinds of what's going to be in the car. All these things are going to be variables, and you're not really going to know until the last minute when the scene is going to be set up. So you're going to have to learn as much as possible about how things move rolling down the hill and then along the ground and the various factors that might affect that motion. The first thing that we had them do was a simplified simulation in which they were trying a game to hit a target. And we did this to learn the basics of CODAP. And let me mention, CODAP is the data analysis environment that we're using, the Common Online Data Analysis Platform. It's a web-based tool which allows us to integrate all these other tools in it. It has a plug-in architecture that allows us to have the sensors go directly into CODAP, to have simulations generate data directly in CODAP. And it provides that exploratory data analysis environment that I was mentioning earlier. We're going to get to play with CODAP in a little bit. I think actually most people on this webinar have done that before, so that won't be new, but for some of you it will be. And then after they've got the basics of collecting data, how to set up, how to do some graphs and basic analysis, they'll actually do an experiment which is similar to that simulation that they did. And they'll learn more now about the noisy data that they're going to generate and the limitations of the instrumentation and what they might want to do in terms of data cleaning or data modeling. The next step, we would do something that's more complex. And in fact, we're going to play with this simulation today, in which there are many more aspects for them to play with than they can easily do in real life. This will allow them to generate lots of data and focus more on this idea of a parameter space exploration. What are the various parameters that affect the phenomena that I'm trying to understand? And so I want to explore those in detail quickly with lots of data. Our next step was then a challenge of pulling together everything they learned about their data analysis, the sensors. This is the case where we had them, the teacher was going to tell them, okay, your car is going to go on this ramp and you need to predict where the thing is going to stop. And so there would be various kinds of things that we would try. Sometimes we'd have experiments or challenges in which different people would be exploring different aspects of the phenomenon. So as in the previous one, there's different parameters that they could explore. Same thing in a physical space, and then potentially come together. And the data sharing is something that we're going to try in a minute, see how it goes. And then the last bit would be them moving on from there. They come up with their own kind of experiment in a related phenomena, but not the same exact one that they've done. Or potentially a new phenomena in which the teacher wants to take what they've learned and then have them design their own experiment. So one of the things that I want to do with a few volunteers here is I want to look at this idea of distributed problem solving and how the tool can also potentially support that. I'm going to jump ahead here. And so we're going to be using the tool called CODAP that I mentioned earlier, Common Online Data Analysis Platform. And we've developed plugins that allow sensors to send data directly into CODAP, and simulations can talk to CODAP and send data in. And it allows for there to be one flexible system for exploring phenomena. This is part of that where I go back earlier to the idea of, the time it would take from you doing my, data collection with sensors and one kind of system that has its own graphing and data analysis, and then I've got my simulations themselves, which could embed their own types of graphs, or maybe I can only run the simulation once and I can't really collect the data. So doing multiple runs, I have to kind of remember how it was behaving. And then oftentimes, even when I do get out lots of data, I don't have good intuitive tools for using that. So CodeApp we're seeing as a central tool that ties together a lot of the ways that students would work when they're doing their own kind of inquiry, and it would help accelerate the type of data collection and thinking and experimentation, sort of tightening that loop. In fact, there's a lot of work that goes into just figuring out what might be possible before I settle into a more formal type of experiment. And CodeApp is a great environment for doing that. All right. Oops. So one of the things that I'm going to do here is I want to show you the simulation first. Don't click on that link yet. Or you probably don't have access to it yet. And you can see here that I've got a car, and the car, I can place the car somewhere here, or I could use this slider to set that. And for ramp angle, I can adjust it using this little knobby, or I could adjust it here. And I can also type in numbers if I want to put in specific numbers. And I can adjust the friction and the gravity and the mass. And if I hit start here, the car will roll down and eventually comes to a stop. And I have a certain end distance. So remember, we're exploring this because we want to be able to make some predictions later about where the car is going to stop. If the director says, put it here, and this is the kind of car, and you understand something about the friction coefficient for that car on this road, and how heavy the car is and which car it's going to be. Gravity, granted, isn't going to change for the movie set, but we have a simulation here, so we can play with that if we think that's part of understanding this whole system. So what I would like is I want to try having 5 of us explore these different parameters, but you would pick one parameter to change and generate data. And it's going to, what we're going to try out is, this might be a disaster, but hopefully not, is we've made a plugin that will allow us to link together these separate documents such that the data being generated by each person's simulation will all go into the same table. But we've got 5 parameters here, so I'm looking for, I'll do one of them, and I guess I'm looking for 4 volunteers then. And so I'm going to go back here, and all right, so
in Zoom if you'd like.
I'm going to do mass. Who wants to explore gravity? And speak up. Tim? Okay. Surface friction?
I'll do that.
Okay. Joan? Ramp angle?
Sean, maybe?
Sorry, who?
Sean O'Connor. Are you volunteering, Sean?
Sorry, I was on mute. Yes, I'm volunteering for ramp angle.
All right, and then distance up the ramp. We need one more.
I'll do it.
Okay. All right, so remember what you said you're going to do. And I'm going to go on to the next slide here. Now, to get to it, you can type this in to your browser, short.concord.org/5v. All right, and so only the volunteers should do that. I'm going to share my screen so you can see what's happening. And when you go, it asks for your name. Actually, don't put in your name. Put in the parameter that you are going to be exploring. So I'm going to explore mass. So I'm going to say my name is mass. So right now, mass is collaborating with gravity. We'll get a few more people in there. And just collect maybe 4 or 5 data points. You don't need to do very fine and collect millions of these. We're just sort of demonstrating here, hopefully, if this will work. So I'm going to oh, I already see some distance data is pouring in. I didn't run that. So that's coming in remotely because we're synchronized. We have synchronized tables. I'm going to start exploring some mass changes. All right, I'm pretty much done here, but we're going to let this go a little bit because it's lagging a little behind because we're generating tons of data. And it's interesting because there's a little bit of there's one little bug here that I'm seeing in terms of this end distance value, which was going to be our outcome value. So that may be a problem. All right, maybe we'll change the question since I did something right before this and I was adjusting some aspect of it, so I may have screwed it up. But all right, it looks like we've got all the data that we have here. And what I'm going to do now is I'm actually going to save this. In fact, I'm going to close the simulation, close the collaboration service here. So now I've got my data about this ramp phenomena. And I'm going to save this, and I'm going to share this out to the whole group so that all of us can participate now. So hold on. I'll call this ramp webinar data. So I'm going to say that. Now I'm going to share this. And this is kind of a long link, but the way we're going to do this is on the next page now. I'm going to put this link here. Oops. And what I would like folks to do is everyone now is invited to play. So this link here will get you to this slide so that you can get to this link. And I'm asking, now I did what affects end distance and how. Since end distance appears to be only sporadically in our data table, I'm going to say what affects the velocity at the bottom of the ramp. So that's the question we're exploring. What people can do is generate some visualizations and put some stuff here. Now I'm going to show folks who haven't used CodeApp a few interesting things. And so I'm going to come back to this. And one of the first things that I actually want to show, which is kind of interesting. Now, I've got data that was generated by lots of different people. But it's sort of like I've got experiments, right? We have the mass experiment, the distance experiment, the gravity experiment. And you see this collaborator run summary here? I'm going to drag this all the way over, and I'm going to make a new hierarchical level. And you can see here are the data associated with each of those that person who is generating it. And so that's going to allow me to actually separate out the kind of graphs that I want to make. To make a graph, I click on the graph button, and now I want to decide. Notice it first just sort of throws all the data on here, and some of it is selected, you can see here. And I've got to configure, what is it that I want to graph here? Maybe I want to graph, maybe I'm interested in a time versus velocity graph. Now this is from all of the different experiments, but maybe I just want to look at the distance up ramp, yeah, let's look at distance up ramp. So I can use this to quickly toggle on and off different variables because it's using this here to set those up for me. And I might say, oh, well, that's interesting, distance up ramp height. So maybe I, in fact, even want to color this by the distance up the ramp, because that will help me understand the different experiments that I did. So notice I'm dragging and dropping either onto the axes or on the middle. And I could take distance up ramp, and if I treat it as categorical, because these were sort of specific values, you can see, now I can look at what happened for each of these distances up the ramp. We could do other kinds of things, like maybe I want to do a graph of the velocity at the bottom of the ramp, right? We said that was one of the things we were wondering about, and the distance up the ramp. So notice I'm doing this now at a different hierarchical level. So there's some interesting data here, and I've got everything again. So I think I just want to, I'm going to hide everything and just show my distance up ramp data. So now that graph makes a little more sense, because otherwise I've got data from other people's experiments beyond distance changes. So that's kind of an interesting piece here. So take a few minutes, everybody explore around, see what kinds of interesting visualizations you can make. Pretty much drag and drop. You can change the hierarchy by dragging stuff to the left or reorder these kinds of things. Those of you who are adventurous, you could maybe think about adding a new column that calculates something. So I'm going to add a new column to calculate the acceleration, sort of instantaneous acceleration. So I'm adding a column, and then I'm going to edit the formula, and I'm going to say, I'm going to put in a couple of holders here and say, I like, let's see, it's the change in velocity over the change in time. So I've got velocity minus the previous velocity over time minus the previous time. And now I've got instantaneous accelerations calculated for everything. And if I wanted to get the acceleration on the ramp, I'm just sort of demoing a bunch of these features so you can think about how you might want to play. Then I can do things like give me the mean of the acceleration, and I can say a filter. I know on the ramp that the x position is less than 0. So now I've said take a mean of the acceleration value that I just calculated, but only where x is less than 0. So now I've got accelerations on the ramp, and I could explore how do these different things affect the acceleration. So lots of different things. We've just scratched the surface of CODAP here, but play around a little bit, and let's go back and see. Make some visualizations and stick them on this page. And feel free to ask questions. I went through that rather quickly.
Hey, Dan, did you see Sean's question in the chat?
I didn't. I'm not going to access the table. All right, so if you click on this link here, that should open the document with everyone's data in it.
Yes, Natalia put that link in there, which I opened up. Thank you.
Yeah. Hi, Tim. So, and you don't have to explore just your own thing. You can, of course, look at all the different factors and either come to conclusions about what you think affects the velocity or the acceleration if you calculated that. You can look at relationships between the behaviors at this level or behaviors at the sort of time step level. Those of you who want to get into doing curve fitting as well by having a plotted function or a plotted value. If you want, you can have movable lines if you think it's linear, and try and do a sort of manual curve fit. although this doesn't look quite linear to me. I don't know that I would use that. But yeah, clicking on the graphs gives you a bunch of other things that you can try as well. And that camera at the bottom allows you to take a snapshot to annotate the graph, and then you could export it and then copy it into our page here.
There seem to be fewer surface friction values than I actually ran.
That's interesting. That's possible. It could be that I cut this off before I got all of the data synchronized. I'm actually very pleased at how far we've gotten without this being a disaster. I was sure this was going to, not sure. There was a high probability of this failing, but it actually worked. So I feel good about that. It makes me want to try it in a classroom. And you can imagine if you were a student and you had to explore all of these things, it can kind of get tedious, trying to do each one separately, and B, this is, I want to, after we get a little bit more time to play with this and maybe put up a few visualizations, I want to talk about the connection to data science, if any, that people see here. Has no one made any interesting graphs they want to share? We could also, rather than paste stuff in here, if people want to share their screen, I can stop sharing, and then you could share your screen and sort of say, here's a cool thing I made, or I have a question about this. I'm not sure how that works or why it looks like this. And I have also experienced probably what some of you are experiencing, which is the sort of flow state you get into in terms of like, oh, I wonder how this works, and I wonder how that's connected to that, and how might I hide this data or use this data to filter other data.
Well, I'll share, I guess, sort of ask a question or for some guidance, and
Sure.
surely would mimic someone else's, but I sort of got going. I had looked at friction, so thought, oh, I want to, explore the relationship between that and some of the other variables. So at first I just dragged on friction and distance from the ramp, and now I'm kind of just experiencing like what should I do next? That gave me the result it did. Where should I go from here? Both in a like inquiry way, but also in like a how do I reset the graph? And so it's just both at once. It's like almost a little, a little frozen, but I'll keep.
Yeah. So we would normally, in terms of setting up the question that students are trying to explore, I think is important. So one of the things that you're bringing up is, just throwing a bunch of data at students and saying, explore this is not necessarily productive, which I kind of did to you. But the question that we were originally looking at was, what would affect the end distance? So this one, and I didn't really emphasize this, was sort of saying, well, what affects velocity at the bottom of the ramp? And so there might be challenges. We actually have velocity at bottom of ramp here. But maybe I wouldn't have given you that. You would have to figure it out from the data. Where is the bottom of the ramp in this time series data? Could I find what the velocity is there? Maybe a formula would help me. Use max of the velocity to find, because I expect it to be going as fast as possible when it hits the bottom of the ramp. So there's kinds of challenges that can be done in which they've got to use the data they have to transform it in order to find that. Or maybe the data is here and what they're trying to explore is these different factors. So they might make several graphs like distance up the ramp versus velocity at bottom, and gravity versus velocity, and mass versus velocity, those kinds of things. Some of the things are surprising, actually. that have an effect. So for example, the distance, the end distance, this is what I was originally going to have us explore. The end distance, it's not affected by gravity. And most students think, well, if gravity was pulling down really strongly, the thing would go super fast flying off the thing, and it does accelerate more. But it also causes friction coefficient to be higher because the thing is, pushing down harder on the ground as it's going. So those things counter each other and ends up going the same distance. So this is sort of interesting things. You get some ability for people to take the preconceptions they have about what the data should be, and then they see what actually happens. And it's really interesting when they have to confront that and have that sort of aha moment. At first, they often think something went wrong. I did something wrong, either with my experiment, or the simulation isn't working, or whatever. And then, after reasoning through it, or talking, or it's a class discussion, or things like that, oftentimes you see the light bulb go on as they're starting to explore the data. So again, that question and sort of what might you do next? So I might, if I were doing a series of these, so here I have velocity at bottom and distance up ramp. So maybe I might say, well, I'm interested in the other factors too. Now I can make as many graphs as I want, or I can just drag over what's there. So for example, if I wanted to look at gravity, I could say, I'm going to drag, I'm going to drag gravity here. And I want to just look at the gravity ones. Oops, I'm going to hide all of these and then click gravity. And so this is my effective gravity on the velocity at the bottom of the ramp. So this is linear, which is kind of interesting. Right, so we might have we might be, oh, maybe it's not. Maybe it's not. I thought at first it was. So this might be one where we're like, that's interesting. So I could click on, so one thing I can do is I can click on this data point and see that this is that run, and here's all the data associated with it. And I might be able to explore, how was this particularly different from other ones? And it doesn't look like, I thought maybe one of the other variables were changed, but no, they're all the same. And so that's interesting. It looks linear initially, but then this last point doesn't fit quite. I might say, oh, well, I'm interested in surface friction. So I can do this. Maybe I turn off gravity, turn on surface friction. And now we've got a very different kind of curve affecting that. So these are ways that I can quickly explore these. I don't know if you imagine if this were done in Excel, like how hard it would be to make lots of different graphs, and the things don't, like if I'm interested in this point here, this quickly jumps me to where that is over here. And if I had other kinds of graphs of the time series, I can also see, well, how do those things relate across graphs? Any other questions or comments, or people want to share their screen, or?
And one question, how did you get distance up ramp, gravity, mass, surface friction into that one table or into that one graph? How did you do that?
You mean these things across the top?
Yep.
So, well, there's a URL parameter that makes this come up automatically, but anyone on any graph could bring up this thing here. It says hide or show parent visibility toggles. So what it does is that feature takes whatever's the leftmost thing and assumes that's the organizing principle for a chunk of your data. And it gives you very quick toggles to turn on or off the sets of data related to that. Right, so I could also make time series graphs that do the same thing. So if I made another graph here and I said I want to look at time and velocity, it's taking a minute. Now, an interesting thing here. So this is all of the time velocity graphs from all of the different things. But notice I had picked this particular run in this surface versus velocity at bottom ramp. And notice how that then highlights the particular run in my other graph. Or if I wanted, I know that this is just, let's see, if this is just surface friction, I could highlight all of these. And now I've picked out the surface friction ones here. So you can see interesting patterns here where we have the linked representations sort of push you on in terms of the data exploration and how you can make connections between the different behaviors that you're reviewing. This is sort of at the top level, right? What's the surface friction? What was the velocity at the bottom? But how did that connect with the behavior of the thing over time at a different level? So partly in InquirySpace, we've been calling this a parameter space reasoning, where I have a parameter that I'm deriving from either my exact settings in the simulation, or if acceleration might be a parameter that is derived from other data that was generated, and explore ranges of those things and how they affect other things, like an outcome variable, like in this case, velocity at the bottom, or end distance, which I'm not sure why that came up the way that did. And over here, I selected surface friction. I could do the same thing over here. If I hide these and just show surface friction, that's going to pull those same ones back up. I can also use a legend as oops. I've got a time delay here. Okay, you can also use a legend. Let's say I wasn't showing these. I could use a legend like dragging these things down here. And now, hopefully, there we go. You can see that I have these different ones here, and I can highlight the mass ones, or the surface friction ones, or the gravity ones. And interestingly, why am I not seeing? Oh, the distance up ramp is hidden, that's why. I've hidden that one. All right, so you can see that I can use the legend itself to highlight different aspects of this. So lots of different ways to explore, generate visualizations. It's relatively quick, so students can, even if they're going down kind of a less than fruitful path, it's not like you have to invest a huge amount of time in that direction. And it gives you ideas. Oh, I wonder how these things might be related. Let me make a graph of this. And so that's where we feel that CODAP, again, that mentioning time, you almost always, if you ask teachers about, what do you want to do inquiry with your students? Do you want your students designing their own stuff? They say yes, but I just don't have the time. And part of that is the data analysis component. And watching kids try and do this kind of stuff, this exploration in something like a spreadsheet is just painful. And you don't also, the other features that you don't get is you don't get these hierarchical structures of data, which is, and we found, I think Joan can speak to this well, because she was part of the CODAP initial project that we're developing CODAP out, some research on how students think about data and how they tend to mentally structure it in a hierarchical way. But spreadsheets don't really make that possible. Right? If you imagine this were in a spreadsheet, we have 288 measurements of distance related measurements. So you would write over and over again, you'd have 288 rows in which you'd write distance, and for the runs themselves, hold on, right, you'd have 288 rows, or you'd have 52 rows that have distance 1, 5, 9.81, 0.3. Like in a spreadsheet, it would just be this long flat table that is harder to comprehend. So I guess I want to toss out at this point. So we're doing, it's sort of like a lab, right? This is high school oriented. They're collecting data, they're analyzing stuff about some phenomena. People have been doing this for a while. Is this data science? Is normal lab work considered data science? Is the way we did this, where we kind of distributed it, and now this more sense making that needs to be done closer to data science? I'm wondering what people's opinions are and the way they think about it. I'm going to stop sharing while we have this discussion. And I know a lot of you are playing with Codec still, so tear yourself away.
Well, it certainly seems like having a whole lot of data and trying to find out what there is to find out about it feels very much like that is, sort of one of the essence, of data science. And obviously it's really a blend. I mean, I was, just to build on what Sean said, I was very aware at the point of trying to explore that you have to actually know quite a bit about the science to know what would be interesting to look at, And so it's a blend of managing and exploring the data with all the intellectual part about what you're actually learning and about the relationships in terms of the science, I wonder if there is there anything that isn't data science about that?
Well, so you could imagine, let's say that we didn't do any collaborative collecting, and it were relatively simple. There were only a couple of parameters. So I just explored it myself, right? That was another example we could have done. So I got a relatively constrained data set. I know where all the data came from because I collected it all myself. I know exactly how it would. It's basically the same thing in a sense, right? I have a simulation, I generated data, now I'm trying to make some sense of it. Would we still consider that a sort of data science-y experience? Are they doing data moves or data science moves?
Well, Tim often has talked about the amount of data being relevant. And I'm not so sure about that. We could define data moves as being all kinds of things. And, from very basic to the more complicated kinds of things you have to do with large sets of data. And I'm still not convinced about how you would ever do a cutoff about that, and what the dimensions are that determine whether something is data science.
Right, I think that's part of the question is, so if I'm doing data analysis, am I doing data science? And is part of that the volume of data, the structure of the data, or the kinds of things I need to do with the data in order to make sense of it? I guess I'm curious about what data science is a little bit of an amorphous term. So I'm wondering, is this more like pre-data science in people's minds, or preparing students to do potential data scientist-like things at a later time? What are the kinds of things that people think are either leaning toward that or maybe feel like it's just regular old making a graph and seeing what it says?
Well, what's the cutoff for what mathematics is? Arithmetic or counting, that's part of math. So that's what I mean about data science. Can be thought of as including a very basic things as well as whatever. I'm not sure how to describe what the higher levels are.
Would Tim agree with you, Joan?
Well, not if he really does emphasize the being awash in data as essential. And I think people who are data scientists professionally are working with very large sets of data, and you know, usually that they have not themselves collected, which is a different task. But
yeah, and doing it collaboratively like this is another piece of it, I think. Like, I know some people who deal with large, unruly data sets, but are often collected by researchers who are on the phone and asking a survey question, which they then input into a shared space. And then, as you know, that could get really messy fast, like depending on how people respond to the survey or whatever, or how a researcher individually might format it. So there's a lot of, I think Tim's last comment before he left was, I feel awash in data, and I certainly do in dealing with this activity.
but I don't know how many head of data scientists work collaboratively, synchronously, or even asynchronously with.
The data set is often collected collaboratively and then is collated into the larger data set.
Yeah, I mean, I think some people would say data science is really about, you know, huge databases of data. You're supposed to be writing, you know, R code to do analysis of it and filtering. If you're not at that level, it doesn't really count as data science. That CodeApp as a tool itself is mostly about, you know, dragging, dropping, and visualizing. So, you know, it's not really data science. I'm trying to play devil's advocate here.
But what other science is defined in that way?
Well, I think it's interesting. I think there's a parallel potentially with computational thinking. And some people think of that as like you're programming. If you aren't programming, you're not really doing computational thinking. And other people will say, well, putting together a drag and drop system model in which, you know, various factors are affecting each other, and there's, you know, looping of the model, even though you didn't write the code underneath or write equations for it. You're doing some computational thinking. You're breaking the problem down into key components and setting relationships up and things like that. I think you get arguments there as well. That again, but it's where do you draw the line, right? I think for some people it's very clear if it's way over here. But other than that, some people want to take a broader perspective on what they would consider either computational thinking or data science, for example.
Well, for educational purposes, it seems like understanding, sort of thinking of it in terms of learning progression or something like that, would be necessary. So then what are if it's not data science, what are the you know, fundamental, more basic abilities and habits of mind that need to be developed that would prepare somebody, you know?
This seems like a parallel argument you're making, Joan, which I would agree with. If a student is doing, you know, elementary math, are they a mathematician? You know, comparing to an expert, and, you know, a pedagogue in math would say you're a mathematician, and someone who's a professional mathematician would say you're learning how to do math and the habits of mind of a mathematician. Mm-hmm. Which in this case, in the physics case, the students are learning the practices of science. Are they scientists? They don't have PhDs. It's a matter of definition, I think.
Yeah, doing data sciences or versus components of data science as opposed to being a data scientist. Yeah.
Correct.
Sorry? I'm sorry. May I say something?
Yes,
of course.
I think I would change the question as it's not, instead of asking, are we doing data science, is, are we understanding data science? So for me, the relevant question in terms of education is if the students are really understanding what they are doing. Understanding in terms of Perkins, in the sense of developing or performancing in different contexts with some flexibility. So for me, it's crucial when you do data science that you have to understand the discipline. You need to understand the context in which you are moving in terms of the discipline, like Helen, I think she said something like that. So for me, it's crucial. We are not if we involve our students in an activity like this one, we need to assure that they are understanding what is going on. They need to know something about the discipline, because if not, they are doing some math, but they are not doing data science. They are not understanding. That's my point of view.
So some of it might be in the way that students are introduced to and engaged in the process, maybe some meta thinking about what it is that we're doing here and how this applies across contexts. Or certain kinds of practices like developing. These are the kinds of ways that we want to go with them having certain data organizing and analytical skills that are sort of the precursors to the more professional data science work, and helping students to see that progression themselves.
Oh yeah, sure. Yes, of course. What I wish to do is for them is to do data science with a purpose. So they need to. You can go and build brick by brick. You make the wall, but to be a a data scientist, you need to do those steps, but each of them involving them with something that they understand what they are doing. That's my point.
Yeah, I think I fully agree with that. And that's also, I would say, the whole NGSS perspective, Next Generation Science Standards perspective here. You know, you can't do the practice without an appropriate context and, you know, potentially cross-cutting concept as well. But that idea of those things, it being critical that you link them together and not try and do them in an abstract kind of form. Yeah.
Dan, did you see Rachel's question as well in the chat?
Oh yeah. So I screwed up a little bit in terms of putting that link there. Let me demo that for a minute. This was I think, Rachel, you're asking, how did I get these things appearing here? Yeah, so I'm going to actually modify the link. Oh, look, we got some cool
awesome
visualizations. All right, if I changed this link here, and there's a feature in there which you can turn it on manually, but I'm gonna change this here so that it will just come up for all of the graphs.
Sorry, guys, I have to leave.
Yeah. So if you click on
Thanks,
this,
Dan.
Yes, hi Joan, very good to see you. If you click on this to open it now, it should, all the new graphs should come up with this. Now notice, I think one of the other things you mentioned is you see how there's all these numbers here? That's probably what you were seeing, because the leftmost column here is this run number. But if we wanted to organize, for example, by the parameter, we could take this and drag it all the way to the left and create a new hierarchical level. And notice these things adapted. So that the thing that's the leftmost thing is what ends up being your sort of your quick toggles for showing and hiding. And so you can create these different hierarchical levels just by dragging over to the left and reorganize. Now, if I didn't use the URL that have this little extra thing added in here, these things are still available, but you have to turn them on individually for each graph. And it's under here, this show parent visibility toggle. But each graph I make, I'd need to do that for if I didn't have this in here. There are basically some scenarios where we think that the analysis is greatly facilitated by having these kinds of things, and other scenarios where it doesn't make sense. So we can decide how we construct the URL we're sharing with other folks to do that or not. I didn't mean to get into that with everybody, though. I was just, I meant to add that into the URL before I shared it with everybody else. So it was a minor disaster, but it seems like it was okay. All right, any other questions? We're actually, we're planning to have this be a shorter webinar than the original schedule. And mostly I just wanted to field if there were any other final questions or comments. And then I would close up here.
I'll go ahead and close for us. But I just want to check one more time. Is there any questions or anything?
So the team, we've got a bunch of people working on this project. A lot of really good people. The main project itself, if you're interested in InquirySpace, the URL to see about the project is concord.org/InquirySpace. And you can email the team at InquirySpace@concord.org. And if you want to email me or get in touch with me in particular with a follow-up question, you've got my information here. If you are interested in learning more about CodeApp, I would go to codeapp.concord.org. There's a lot of great information there. And I should thank Christian's here. And Christian did a Spanish translation for us. So if you want to use CodeApp in Spanish, you can thank Christian here. We appreciate it very, very much.
Thank you. Thank you. Rachel and Christian, looks like you both have some things to say. I'm going to ask Rachel's question first, which is I'm curious how this has been used in classrooms and if it's integrated in curricula. Maybe Tom and Dan can tag team that answer.
So CodeApp itself has been used in many different projects now. And depending on the project, it's either tightly integrated with curriculum or sort of more loosely used as a tool as the teacher decides they want to just, they're replacing their spreadsheets basically with CodeApp. It's very easy to drag and drop data into CodeApp. For InquirySpace, we are tightly integrating it into curricula, and we're developing those on-ramps I mentioned earlier regarding how to get people to the place where they have those design, collect, analyze, and explain type skills. And that CodeApp comes in at key moments throughout those curricular steps or phases of the curriculum.
And Rachel, I would add to this that in both InquirySpace and other projects that I've been affiliated with, when we describe and show and allow teachers to explore CodeApp, it always is the highlight, if not a top highlight, of their experience. So this has been a very powerful tool that teachers are grabbing onto.
I'm also I just want to ask Christian, you have a suggestion? Did you want to talk about that?
Oh yeah, I would suggest I would like to use net logo simulations with CodeApp, and I saw Kit posted some slides, and I asked him to repost them because they were not so clear. So just to say that for me, and I think for other teachers, it's crucial to include some of the net logo simulations in with CodeApp. So please help us to have again the whole process on how we can do this.
Yeah, so that in itself is interesting. Uri Walensky was part of the original InquirySpace project. And And so we did a lot of work with them in terms of getting a web-based version of NetLogo, which is necessary for it to plug into CODAP. At this point, we've done some additional work in which they've built in special commands for us to be able to talk to CODAP. So it's possible, but it's sort of on an individual NetLogo simulation basis, and one has to have the know-how to modify the simulation to tell it and output these variables to CODAP and when to do it. So it's a little bit of a manual process now. It can be done. We had been talking with them about having a sort of default where it could check to see, am I dropped into CODAP? If I am, then I'm going to put out, by default, some stuff, all of the sliders and any graphs that I have, I could put out to CODAP. And Uri has said he is interested in that, but it's a sort of a matter of priority. They're continuing to develop out NetLogo Web to have more of the full feature set that the Java, NetLogo app has. So someday, I'm sure that will happen. If the extra work is to be done for a particular one, that can happen now, but it's not straightforward, like you mentioned. I will mention that all of the Concord Consortium lab-based interactives, the molecular workbench interactives, all do talk to CODAP. So you can not just drop them in, and they will generate data automatically. So there's a whole set of simulations there. They're not the agent-based ones like NetLogo. They're more molecular dynamics simulations. But those should work.
Thanks, Dan.
There was a question about South Texas classrooms in Spanish. So the Spanish translation is relatively new. And I am not working with any particular classrooms there right now in terms of projects. A lot of our direct teacher work is primarily through projects that we have going, where we have research cohorts that we're working with. So I don't have any teachers that I'm working with in South Texas now. But Christian, why don't you explain why you wanted to translate it into Spanish and how you've potentially been using it?
Rachel, do you see Dan? She writes, Dan, I see you're also part of the SAGE modeler, which is also mentioned. I'd love to learn more about this too.
Yeah, so I don't know if Christian wants to answer that original one about Spanish first, and then I can answer about SAGE modeler.
Yeah, sorry.
Sorry, say it again. What is the question?
There was a question. I think the person has left, actually, so maybe we can skip it, but he was basically asking about how we've seen the Spanish version working with students and teachers.
I haven't used it yet with students, but I gave a workshop with teachers, and everybody was very comfortable. They felt comfortable working with the Spanish version. We also worked with the Spanish translation that I made with the examples. So now, if you have a CODAP set up in Spanish, when you click on Open from the CODAP main menu, you'll have access to the Spanish examples. I also translated the ants, the picnic ants, the ants activity. So there are some, and I'm planning to translate more examples. So I don't know yet if any, because I don't do classes. I train teachers, so I don't know if. And the workshop was like 3 weeks ago, so it's a little bit early yet to see how the teachers are using the Spanish version with their students.
Yeah, so this looks great. I'm demoing here the Spanish version. Notice the flag up here. You can see the different languages that we have, and you've translated this particular data set and all the text.
Yes. So if you go to the main menu and you click Open, or you click Abrir, it's open, you will see mamíferos, 4 elefantes marinos, 4 seals, and mammals, and yeah, and picnic areas. So
Very
you will
nice.
have there all the data in Spanish, all the guides also. If you go to picnic and picnic.
Yep. And you know, I believe we actually have an ant net logo model working in CODAP.
Yes, yes, you have.
All right. Well, we thank you very much for that, Christian, and would love to hear how this ends up working in terms of the Spanish version.
No, and I would love to travel to Texas and participate in a workshop with teachers to teach Spanish-speaking teachers. So,
well, if we have a project there, I will keep you in mind.
thanks so much.
And Rachel, regarding your question, yes. So Sage Modeler is one of my projects. We actually designed it as a plugin to fit in CODAP, so that it could generate data into the CODAP environment, and we could pull in other data sets. So students basically design system models. The model can generate data, and then they can bring in either public data sets or experimental data or some other professional simulation and compare their output with other data sets. Again, one environment allowing them to do all that comparison. I can't remember if we have a recorded webinar about Sage Modeler or not.
We haven't done a data science education webinar on it, but we might have a recorded round egg that may be possible to share. We'd have to check.
Yeah, I can look into that and see if we can get back to you about that. But at some point, if you're interested and you want sort of just a personal tour, you can connect with me and I'll show you around Sage Modeler.
Wonderful. Dan, can you share your slide again with the email address, just so Rachel sees that?
Yes. Where am I? Here I am.
Okay, lots of great
All right.
today. Wonderful. Okay. Without any further ado, I'm going to go ahead and wrap us up. And I'm going to steal the share screen from you. Okay. And thank you again, Dan, for sharing your work on InquirySpace, and to everybody who joined us today. Thank you very much. If we did not get to your question, or if you think of something after we're done, go ahead and send us an email. We're at dset@concord.org, or you can email Dan at ddamelin@concord.org. We have lots of great interaction. I'm grateful to all of you for making this such a rich discussion. I will send you a link to the recorded session shortly. And if you enjoyed this webinar and you'd like to attend a future data science education webinar, our next webinar is on June 25th with Walking and Goal. You will be beaming in from Germany to talk about a pro-civic stat project, and I'll send some details shortly about that. You can sign up for future webinars at concord.org/meetup. You can stay connected with us on Twitter at CodapDataSci or at concord.org. If you use the hashtag DataSciEd to tweet us any additional questions or resources, we will be happy to respond to you. Please feel free to visit our website. We're at concord.org/meetup, and CODAP is at CODAP.concord.org. Look forward to connecting with each of you again soon, and thank you all very much.
Thanks a lot.
Bye.
Thanks, Dan. Thanks, Talia.
Thank you.